Hi, everybody. This is Matthew Poes of Poes Acoustics, and we're going to be talking about two different methods that can be used to deal with bass modes in a room, and doing a little bit of analysis using a tool that many of you are probably already familiar with, which is the Room EQ Wizard's Room Analyzer, or Room Simulation, I should say. So I'm going to add my screen. Here we go. Now, hopefully you all can see this just fine. What we've got right now is a pretty typical installation that we would see, in which I've actually done these as if they're like in-wall speakers because I wanted to get rid of the effects of the left-right speakers. And instead, what I wanted to do was show you what happens when you place a person in a room like this with seats on either side of them. So we've got microphone positions that show seats up against the back wall, seats to the left and the right, and then the listening position. If we look here, remember that we're really mostly interested in what's happening below 80 hertz for this subwoofer work that we're doing, because getting into room treatments can be tricky. Now, I've set the surface absorption to around 0.25 for all the surfaces except for the floor. And the reason for that is that typically most of your walls are going to be, even if they're bare drywall, having an absorption coefficient at low frequencies of around 0.2 to 0.25. That's pretty normal. If you've put 2 to 4 inches of fuzz on your walls, even though they don't absorb a lot at low frequencies, at these sub 100 hertz frequencies, they do absorb some. So you could go up to 0.3 or 0.35, something like that. Remember, it's the average of the total surface area. So you would assume that your walls are somewhere between 0.15 and 0.2. That's if you have drywall walls sitting over studs. If you have concrete walls, it's probably like 0.1. You can assume something really low. But assuming typical, at least American construction, where you do have drywall over studs, or if you're in Europe or the Middle East, something like that, the steel studs are a little more common if it's not concrete, and then with drywall. So you're going to get some absorption, and that helps to make some of these reflections a little less strong. There's a little bit of damping. So you do want to account for that. But you can see that when we look below 80 hertz, because remember what we're seeing here, this is not normalized. I kind of wish it was, but it's 105 here, 90 here. Call the average level about 100 dB, right? Well, if the average level here is around 100 dB, then we're seeing variations in places that are as much as, so what is that showing up as? 63 dB. So 37 dB variance. Same thing with some of these peaks, or troughs, I guess I should say. Even the more shallow ones are pretty bad. So within the variance of the space, we've got quite a bit of variance that we want to look at, right? Well, so we can, there's a nice quick fix that addresses most of these issues. Many of you have heard this. Harman had promoted this based on some work that Todd Welty had done. And there, you can do a more complex version of it. But if you have a standard cuboid room and you stick 4 subs in the corner and you get everything time aligned correctly, which we're accounting for here, then you can see that as we add more subs to these corner spaces, things start to improve. So let's look at this again. We add this. Okay, well, actually, that made some things better, some things worse. So this got a little better. This got worse at some of those positions. Main position, though, didn't really change. That's the behind position, I should say. Sorry. So the main position is going to be the white one. So we add this. All right. So some positions got worse. Main one didn't really change. Add a third one in. Oh, just by going to 3 subs, we saw a significant improvement in the variance. This is a very EQable response. It's not perfect. There's still problems, but it's much better. Now, if we go and we add a 4th sub, look at what happens. Wow. So now it's way better, all the way up to, where are we, around 55 hertz. We still have some variance up here. It's still better than it was. And it's going to need some EQ to get things nice, but it really, up to 80 hertz isn't so bad anymore. Here, it's nearly perfect. There's like very little issues. We have a little peak based on that's the first mode of the room. So that first mode is going to be something based on the length of the room. It's happening right around 30 hertz. The neat thing about that is that's fixable with EQ, because there isn't a lot of spatial variance there, just a little bit. What you're seeing here is that the front seat positions are basically identical to each other. And so that the EQ will fix that. The back seat, you're seeing what happens when there's the seat is pushed up against the back wall. So there's an accumulation of the low frequencies. Now that's based on this seated position with the subs in these locations. You could move the seats. So for instance, we could do something like this, and we can start to see that it's not so perfect anymore. So you do want to pick your seating positions carefully in a situation like this. What if we do something else though? So right now we've got the subwoofers in the corners. What if we were to move this subwoofer here to around the, call it, quarter point, and we move this one over to the quarter point. We're doing the back wall ones, right? We're going to move these over to the quarter point. All right, and we're going to move this one over to the quarter point. So interestingly, this really made things a little bit worse in certain situations and a little bit better in others. So some of the stuff up here got a little better. This got really a lot worse. This stayed the same. In fact, it's not going to fix it. Well, there's actually some additional things we can do. We can add more subs. So we're going to add 2 more for now. Oh, come on. Here we go. Gonna make it. So I'm going to move this one up here. We're going to put it at the quarter point. All right. And we're going to take this one and we're going to do the same thing. Doesn't need to be exact. Move this up to the quarter point. Move this up to the quarter point. All right. So now look at that. We have no spatial variance at all. What we have are a bunch of peaks, yes, but no spatial variance. All of this can be EQ'd. That's the neat thing about this. Now that we've completely eliminated the spatial variance, we've got this situation where we can actually get into EQing the system flat and not worrying about it. So while you might look at this and say, well, there's all these peaks caused by the modes. Yes, there are. Actually, there's no real issues that can't be easily EQ'd out. So this is showing what happens when you get into base arrays. And the interesting about this particular example is that there is no base array being used on the back wall for this one. It's still 2 subs on the floor at the quarter point. What we're doing instead is using them on the front only to eliminate the effects of some of the modes. So we've basically eliminated most, if not all, of the spatial variance, and then put ourselves in a very EQable position so that you'd have very little difference between seats. And you might say, okay, but what if your seats are farther apart? I mean, how good is this? Well, actually pretty freaking good. If we look at the microphone positions, we can even increase this to 4 feet, 4 feet. All right, just look like that. And we're looking pretty good. So this particular one to the left is a little bit worse. I think I probably don't have things placed exactly right here. So this one is, all right. You can see, by the way, how, like, look at that. We can play with it and actually kind of fix some of the issues by moving it around. But there's also another possibility. Oh, I see what I did wrong. Those were not where I wanted those. I moved the wrong ones. But actually, that didn't really fix that problem much, but we do still see very little variance. The point is you're seeing that the base arrays are making a big difference. If we go to the speaker positions, oops, speaker controls, here we go. We can add even more subs. What was I playing around with? Oh, wait. That would have helped. Didn't realize I did that. All right, they need to all be sealed. But you can add more subs. So we just added 2 more subs. They're here. We don't want them there. That's not a good location for them, right? So we're going to turn them in the right direction. Ooh, what did I do? We want them this way. And we're going to put them over here. Actually, we'll put them here for no, here's good, actually. Yep. And then wrong direction. There we go. Over here. And then we can put them here. Here. Look at that. Now, with the exception of this one little mode here, everything is basically perfect. We've kind of completely eliminated these issues. Everything is not sealed, though. Let's fix that. There we go. Now we fix that problem. That was an issue with the porting. So you do have to be very careful that you don't introduce other phase anomalies, phase rotation, which ports and sealed. You were seeing the effect of what happens when you mix sealed and ported subs. All right, there we go. So now you can see how this looks. And now I understand why I was seeing weird results. I kept accidentally lowering the LF on these. They can be different, by the way. Like, watch this. We can take this and make these. One can be like 15, and then we can make this one 15, and we can make this one 45, and this one 45. And you're going to see it affects things a little bit, but not much. And so mixing sealed subtypes is not a huge deal, even if they have different bandwidths, as long as you don't have filters in there. Filters can really affect things quite dramatically. In any case, you can see here what we've done. Now, one of the interesting things is we do still have some modal issues, like this mode here and this mode up here. And this is where we get into, so this is the basis for what waveforming works off of, but this is not waveforming. Waveforming is not just a base array. Waveforming is more than just a base array. It relies on a base array as a way of giving it an easier platform to operate on, but it provides special separate EQ to each of the subs. It also provides special signal processing to each of the subs that allows it to steer the bass. So you can think of it more as something that uses line arrays, in a sense, bass line arrays, that create planar waves, which can then also be processed to create beamforming. And so it's like low frequency beamforming, which is completely doable. And so it allows it to have the spatial control that typically would be impossible for small room systems like this. But once you do that, these little peaks here, you can actually mitigate those even further to reduce the need for a lot of EQing. There's still going to be EQing, don't get me wrong, but it reduces the need for that quite a bit. And what happens is you end up with a system that's quite flat. However, it's always going to be bandwidth limited by the distance between these subs. So we've already done this system with just 8 subs. With beamforming, because of how it can work with the rear array, we could actually move those rear subs to the front and add an extra set of degrees of freedom to the control. That would give better bass control. I don't think the simulator would show those results very well. But what you can see is that that's only going to work up to around here. So what's going to work above here in this area? Something else. And that is where the very simple way of looking at it, you can just look at the anechoic response. Look at that. So if we were to go and change, because what's affecting this to be 0.5, and we just do that pretty much across the board. We make this 0.5, and we're going to raise the floor to 0.25 because we're going to say, well, we've got, I don't know, a floating floor and some carpet, and we're going to make the front wall 0.5, which will help with some of the stuff a little bit too. Look at that. This damping that we applied actually smoothed all that out. This is where the benefits of room acoustic treatments mixed with a bass treatment approach like we've been talking about here becomes useful. The bass treatment approach that we're applying, one of the problems with the way this is done, by the way, is that it's applying an average absorption coefficient, basically an average amount of damping at all frequencies. It now thinks that there's 0.4 absorption all the way down to like 1 hertz, and there's not. That's just simply not true. So that's why all of this started to get even closer together and smoother. It's not going to add that much down there. There's no way to make bass traps that can do that. However, the reason I did this to show you was because you could see the improvements it made up here still, which were quite significant. And in fact, at 200 hertz or even 150 hertz, we can get much higher absorption coefficients than 0.5. We can potentially have walls whose average absorption coefficient in that range might be something like, call it 0.75. And so that's the back wall, the left wall, and the right wall. And so again, we can start to see that we get even further improvements. And of course, the front wall could have that. It gets a little tricky to do that. And the ceiling, let's see if we can do it to the ceiling. No, actually made things worse for whatever reason. Anyway, you get the point. We're seeing improvements here because that space is starting to look more anechoic-like because of all that absorption. What would happen, though, if we applied an average of 0.75 across all the walls, that means you've covered more than 20% of your walls with absorption. And if we used standard absorbers, meaning just like fiberglass mineral wool foam on the walls, and that's how we did this, the problem you're going to quickly run into is that the room is way overabsorbed and way too dead. Your bass is going to look better, and it probably is even going to sound a bit better, but everything else is going to be worse. And so the better way to handle that is to use bandwidth limited absorbers. And there's a number of ways that can be done. So you could take pegboard and put it over fiberglass, for instance. I've actually recommended that to people before. The positive of that is that it becomes like a low pass filter on the absorber, and it reduces high frequency absorption, but it's not going to take you all the way down to 200 or 300 hertz, which is really where you'd want it to be. And the other problem is that that's a periodic pattern. So it's going to create some issues with the way sound reflects off of it. And if you look at the patent for the binary amplitude diffuser that Peter D'Antonio developed, you can actually see why having a periodic hole pattern like that can be problematic for the reflection. So that's not ideal. You can create a binary pattern like Peter did, and that's a better approach because that's going to be allowing for better reflections. There's a little bit of diffusion. It's just a better pattern for doing that kind of low pass filtering of it. And in fact, there would be some things you could do to further improve the low pass filter. You could add a membrane below it, for instance, or you could change the density of the materials and the surface texture to allow for something that has even less mid-high absorption. The other approach, of course, is just to use a membrane absorber, which itself creates that. And so that then becomes an absorber. And I kind of like the dual approach of having something that's bandwidth limited with a plate, but you could just do it with just the bandwidth limiting membrane over the front of it. Or the other thing you could do is you could mix Helmholtz resonators or membrane absorbers that use things like steel plates and have them tuned to different frequencies that all work optimally. They don't really, I think people sometimes get the idea that these things work all the way down here. You can make a Helmholtz resonator that works at like 30 hertz. You know, if you want to, give it a shot. It's going to be huge. I think the better thing to do is to focus on the reflections that are up higher here because they can be much smaller. And so you could scatter little Helmholtz resonators all over the walls. You could put in, again, like steel bass traps in different locations. They need to be pretty sizable, but you could tune them to different frequencies that range somewhere between 80 hertz and 200 hertz. They don't have to be that big then, and it gives you good results doing that. So these are ways of mixing acoustic treatments with different bass array approaches. But you know, the one thing that's interesting about all this that I want you to see is that when you look at all this, if we start to then get rid of all these subs, that response is going to progressively get worse until we get back to this. And again, remember, this is way higher in those ranges than we really want. You could do that with full acoustic treatment, but most of you don't have anywhere near that. So if we go back to numbers that make more sense, like this, then all of a sudden we see the real variance that we've got going on with just one subwoofer in this particular location. This is floating off the ground. Here's the 1/4 point. Here's moving it to a corner. Other corner, different places around the room. Notice that it's kind of hard at different places around the height of the room, I should say. I mean, here's one that actually has it's interesting. Just one sub is actually giving us a pretty good response, but look where it's located. It's actually like up in the ceiling area. Apparently, if you put one subwoofer dead center up on the ceiling of this one, it's showing a pretty good response with just a dip here as a result of this mode. And what you could do then is EQ this down, EQ this down, EQ this down, cross everything over, and you get a pretty good response. I don't believe that's going to work if we put it down here. It's pretty close. Yeah. So this is showing the value of doing something called a subcrawl, where you can move it around and find locations that might work well for your particular seating position. Remember that the moment we start moving these seats around, you know, whether this works or not, it's going to change quite a bit. A lot of times people end up sticking their seats right around the 50% mark, which is can cause problems. In this particular location, we're seeing it actually works pretty good. So here it causes here terrible problems. Here it actually looks pretty okay. You could probably work with that. That would be acceptable. But the other, of course, issue you have with these subcrawl approaches is, can you put the sub there? Is there a TV there? Is there your processor there? Is there no way to put a sub there? So sometimes we have to make do with what we can do, and it's easier to put subs around the room in different locations. You can also end up with bigger rooms, which can then create problems for this concept, where the room is so big that none of this is going to apply in the way that we're showing it here. Anyway, it's not the point of this video. I just wanted to show you for most of the rooms, you guys are dealing with some different ways to handle the bass. So actually, I guess we covered 3, not 2. The 2 that I was trying to show you is what some call the Welty approach. the bass array approach. And then this is actually, I would call it the sub-crawl approach, which is, it is in fact possible to use one subwoofer and get pretty optimal bass in some rooms, especially cuboid rooms. But it is tricky to do that. And often the problem you run into is that to find the one location that's good requires a particular ratio of dimensions for the room. This room happens to be ratioed pretty okay. And pretty optimal placement of the listening position and the subwoofer placement. And often it's just not possible to do that. And so this doesn't really show you what you want to see. So, all right, hopefully that was helpful. And I just actually realized after telling you all that, something happened to my microphone position. One of them does not look right. Behind the main, that should not be 4 inches. That should be 4 feet. There we go. Oh, no, not 4 feet even. It should be 6 feet. Typically you're 6 feet. So actually that position doesn't work so good for the backs. So for one row, we were able to move the sub around and get a good position. Let's do that again and show. But it looks like there is no way to get really good low variance bass for multiple rows of seats with just a single sub, which I was surprised to see that. I didn't realize it reduced that until I saw the mic was moved. And like I said, often we're kind of looking at something more like this for positioning. And you can look, that looks awful at that point, which is actually what I would have expected. There just isn't a good position that we can do that. You can also get it back on the ground. And then of course you can move it around like this, trying to find that one good location. The other thing I'll mention is that even though bass is non-directional, it does seem like when your bass is like over here, it sounds like the bass is coming from there. And so there's other effects that can cause that. So having arrays on the front with some, we'll call them control bass modules on the back, can give the effect of having the bass come from the front, which I think is better than some of the other approaches. Anyway, hopefully this was useful. Please like this video if you liked it, subscribe to my channel, and put any comments below that you have.